Welcome back. In the last session, we had seen DC analysis of differential amplifier. Now let's see AC analysis part. I already explained with respect to the circuit diagram. When you apply the DC voltage, then I'm expecting IC is equal to IC by 2, I bias by 2. When you apply the differential input, what is differential input? When V1 is increasing, V2 should decrease. When V1 is decreasing, V2 should increase. Therefore, this is what is called differential input. Okay. For this input, you will see the change in output voltage. If input is changing in a common mode manner, then your output voltage should not change. We don't want the output voltage change like V01 or V02 change with respect to V1 is equal to V2 when both are changing at the same time. When V1 is opposite to V2 or V2 is opposite to V1, then only we are expected to see the change V01 and then V02. This is what I explained in the last class. Now let me explain how the gain of differential amplifier is same as common emitter amplifier. Okay. Now if you speak about AC circuit, okay. Now this is what your complete circuit. Now if I speak about AC circuit, what is AC circuit? Now this is what is AC ground. When I say this is what is AC ground, then this is nothing but common emitter amplifier. This is also common emitter amplifier. Both are common emitter amplifiers, right? Therefore, if you ask me AC circuit, because your VE is connected. What is VE? VE is constant with respect to the V1 and V2 which are shown. When VE is constant, then this is nothing but where delta VE is equal to 0. Therefore, this is what is called AC ground. This is what is AC ground. Therefore, if you ask me, the circuit will become, this is AC ground. Similarly, this will be AC ground. Now I can say this is what is the V1, which is small v1. I am not showing the common mode voltage because only AC circuit, only AC signals we need to see, not the bias signals. And this is what is VCC, same VCC. This is RC. Now let's see small V01 and this is small V02. Right? This is what is Q1, Q2. This is AC ground basically. This is also AC ground. Right? And if you ask me, this is nothing but your common emitter amplifier. This is CE amplifier. This is also CE amplifier. Then what is differential gain? Differential gain definition. The differential gain definition, either you can take this or this, anything is fine. The differential gain is defined as AD is defined as output voltage V0 divided by, okay, VD, small VD. If you ask me what is V0, V0 is nothing but the difference of V01 and then V02 or V01 and then V02. Therefore, this is nothing but V01 to V02 difference divided by V1 to V2 difference, V1 to V2 difference, V1 to V2 difference. Okay, mathematically I can prove. What is that? Tell me the relationship between V01 and V02. Let us say this is what is the signal what you want to amplify. Therefore, this is the signal what you want to amplify. Then exactly opposite to that we are applying here. Exactly opposite to that we are applying. Therefore, what is V2? V2 is equal to minus V1. Therefore, what is V2? V2 is equal to minus V1 or V1 is equal to minus V2. Anything is fine. Then what is your output voltage? The output voltage V01, right? This is what is the signal after amplification. It is having inversion. That is what your common emitter amplifier. And what is the output voltage here? Okay. This is what is having inversion with respect to this. Okay. Now what is the relationship between V01 and V02? Your V01 is nothing but minus V02 or V02 is nothing but minus V01. Therefore, what is V02? Your V02 is equal to minus V01. Okay. Now if I take like this, okay, therefore now tell me, now if I take it, then tell me what is AD. AD is equal to V01 minus, what is V02? V02 is nothing but minus V01, exactly opposite to it, right? Minus V01 divided by, what is V1? Let us say minus, what is V2? V2 is equal to minus V1. Minus V1. Then what is this? This is nothing but 2 V01 divided by 2 V1, which is V01 divided by V1. Or if you calculate, what is V01? V01 is nothing but minus V02. Therefore, if you do that, you will get V02 divided by V2. Therefore, the differential gain AD is same as differential gain, differential amplifier gain, differential amplifier gain is same as single-ended amplifier gain. Therefore, what is single-ended amplifier gain? If you take AD, let me take mod AD. If you take simplified model, HFE into RL divided by HIE, or what is HFE divided by HIE? GM into the load. Maybe load is nothing but RC here. Therefore, you can take it as RC. This is RC. This is also RC. Okay. This is what is our gain. Your differential amplifier gain is same as single-ended amplifier gain. Therefore, you are not getting any extra gain and you are not losing any gain. Whatever gain you got from single-ended amplifier or simply common emitter amplifier, the same gain we are getting, but remember this gain is referred to differential gain. Okay, because we have something called common mode gain. Therefore, differential gain is different to common mode gain. Whatever gains we got, like the voltage gain, current gain, etc., that is what is referred to here differential gain. Okay, we are looking for differential gain. We don't want common mode gain. We want to reject common mode signals. That is what is making Q point stability. Okay, take it. Then I'll explain the same thing. Using waveforms. Then it is easy to understand and it is easy to remember also. Okay, saying that the differential amplifier gain is same as your single-ended amplifier voltage gain. Okay, then no need to derive again, because once you know that differential amplifier gain is nothing but your single-ended amplifier. When I say single-ended amplifier, what do you mean by single-ended amplifier? CE amplifier. Therefore, when you say single-ended amplifier, this is CE amplifier. Take it. I'll give you 2 minutes time. This is already explained in the last session. Now this is what is extra, saying that your AC gain, which is differential gain, is the same as common emitter amplifier gain. Okay. Now let me erase everything. Can I erase? Now the same thing I'll prove in a different way, and this is easy to remember also. Just don't write anything. Just for your understanding, we know that this is common emitter amplifier having gain of 100. Okay, if that is what is the scenario, let us say this is what is time axis and this is the input which is to be amplified. Let us say this is what is the input what you are applying, this is what is V1, okay. Maybe I can explain with respect to this. We have VCM plus this thing, right? Therefore this is what is our capital V1, this is capital V1. We have VCM also. On top of VCM you have the signal what you want to amplify. Therefore tell me if this is what is the signal, what is your output? Your output will be, right, the corresponding time. Let us say this is time, and now this is what is capital V01. Then we have VOCM. We have VOCM. Okay, this is what is VOCM we have. Then on top of that, when this is what is the input peak to peak, then you will get output peak to peak, something like this. Let us say this is what is after amplification. Okay, the space, this is not enough. What I do, this much swing, this is okay. Now let us say, but if you compare, this is what is your time, okay. For this input, let us say this is what we are getting, and now this is what, let us say this is what is some peak to peak. For your understanding purpose, let me take a 10 millivolt peak to peak. When you apply, or 1 millivolt peak to peak. When you apply 1 millivolt peak to peak, because we want to apply small signal, therefore 1 millivolt peak to peak. Then let us say if gain is 100. If gain is 100, single amplifier gain is 100. Therefore your common emitter amplifier gain, let us say, let CE amplifier gain for AV is equal to minus 100. Minus is there, right? Therefore minus 100, that's the inversion is there. Then what is output peak to peak? If input is 1 millivolt peak to peak, then your output is, this is 100 millivolt peak to peak. 100 millivolt peak to peak, because the gain is 100. Okay, your gain is minus 100. Now let us apply V2. Now let us say this is V2, where the common mode signal is VCM. Okay, now exactly opposite to this we need to apply, then only it is called as differential input. Okay, then only this is called as differential input. Let us say this is what is applied. Now if you ask me the peak to peak, here also I am applying 1 millivolt peak to peak. 1 millivolt peak to peak. Then tell me what is your corresponding output. Let us say the corresponding output, this is V02, where it has VOCM. This is output common mode. Then what is your output? Your output will be something like this. Okay, let us say the output peak to peak, right, is also 100 millivolt peak to peak. This is also 100 millivolt peak to peak, right? When you give 1 millivolt peak to peak, you are getting 100 millivolt peak to peak. That is what is stage 2. This is also common emitter amplifier. This is also common emitter amplifier. Now for the differential amplifier, the differential voltage VD is nothing but V1 minus V2. Therefore now let's see what is VD. This is post processing. This is what is actually, therefore now tell me what is our VD. Now VD differential voltage is equal to V1 minus V2, right? Therefore tell me what is the common mode voltage, VCM minus VCM, that is 0. Now what is your input peak to peak now? Let me give you a different color, right? Now what is this? When this is what is peak, let us say this is what is 0.5 and this is what is minus 0.5. 0.5 minus of minus 0.5, 1. Therefore you will be getting, this is what is your input. Therefore if you ask me what is your input peak to peak, your input peak to peak is 2 millivolt peak to peak, because VCM plus, let us say 0.5 millivolt and VCM minus 0.5 millivolt. Here VCM plus 0.5 millivolt and VCM minus 0.5 millivolt. Then tell me VCM minus VCM 0. This is 0. Now 0.5 minus of minus 0.5, then it will become 1 millivolt peak to peak, 1 millivolt peak. and minus 0.5, minus 1 millivolt. Therefore, remember the DC voltage whatever you have, right? That is what is on top of VCM. Therefore, this is VCM plus 0.5. This is VCM minus 0.5. Similarly, this is VCM plus 0.5. This is VCM minus 0.5. But if you take here, this is nothing but 0, simply 1 millivolt and then minus 1 millivolt. It is what is becoming like AC signal. Okay? I just am explaining DC plus AC, right? Now, if you see here, let us say this is what is VOCM minus 50 millivolt and this is VOCM plus 50 millivolt. Similarly, VOCM plus 50 millivolt now minus VOCM minus 50 millivolt. Okay. Now tell me, what is your output now? Your output is nothing but time, right? So if I take this, now what you will get? Let us say, what is VD? V0. Now your V0 is equal to difference of V01 to V2, V02. This is the difference. Either you can take V01 minus V02 or V02 minus V01. If you take V02 minus V01, you will get same phase. Then input and then output will have same phase. That is what which is defined in the op amp. Therefore, now if you take V02 minus V01 or V01 minus V02, anything is fine. Then you will be getting the same swing. But if you ask me, this is nothing but 200 millivolt peak to peak. Why? VOCM, that is 0, then minus 50 plus 50, therefore minus 50 minus 50, this is minus 100 millivolt, and here plus 50 minus 50, this is plus 100 millivolt, this is plus 100 millivolt. Therefore, tell me what is your peak to peak? Your peak to peak is 200 millivolt peak to peak. Because I don't have space, remember this should be double of this. You decrease the swing, then it will tell the story. Because it became bigger. If you decrease, okay, this is what is our, this is VOCM minus 50 millivolt. Then this is more, okay, that's fine. This is VOCM. Take it. Therefore, tell me what is your gain now? Differential gain is defined as, therefore tell me what is differential gain? AD is equal to, what is V0? V01 minus V02. Therefore, V0 divided by VD. Therefore, what is V0? V0 is nothing but 200 millivolt peak to peak divided by, what is VD? 2 millivolt peak to peak. Then what is this? If I take only magnitude, right? That is what is your AD. If you take magnitude, right? Therefore, what is this? This is 100 only. What is 200 milli by 2 milli? Because whatever input you are giving V1, we are getting output. But we are giving opposite to it, that is nothing but your second input. We are getting again output. But if you take V01 minus V02, you may say that your output swing is increased. But remember, your input swing is also increased by means of VD. Therefore, don't think that your gain will increase, because when you do V01 minus V02 or V02 minus V01, your output swing is increasing, which is 200 millivolt peak to peak. Right? With respect to single stage, it was 100 millivolt, but now 200 millivolt. But remember, when I say 100 millivolt, that is with respect to 1 millivolt peak to peak. But now 200 millivolt with respect to 2 millivolt peak to peak. Overall, the gain is constant only. Okay? It is not changing. Take it. This is what is our gain. If I take magnitude, that is 100. Therefore, the differential gain is same as signal gain. It is not changing. That is what I want to say. Mathematically also we can prove that, and using waveforms also we can see that. Okay. Try to represent. These are all little bit bigger, right? to sine wave only. Okay. Now this is what is your output. What I'm doing, make it thick. So it is easy, and later on it is easy to refer. For here it is, we are defining, let us say V01 minus V02, then you will get this. If you define V02 minus V01, you will get opposite to it. The phase is known to you, right? Why we are getting negative phase and all, that is fine. Therefore, the gain is not changing. That is what I want to say. The gain of your differential amplifier is not changing. Actually, we can do some mathematical analysis, but again you will get the same answer. Then why to do? Instead of that, we can invest some time to solve the problems. Means to get the differential gain is equal to signal gain, whatever I told before, which is HFE into RC divided by HIE, right? If you take simplified model, then we will get the same thing. Not required. Enough. Then after this, immediately we can go for practical differential amplifier. Okay? Or I'll define, because for the same differential amplifier, we defined common mode gain and we got 0 because of current source, and differential gain we got same as common emitter amplifier, that people define something called common mode rejection ratio, which is differential gain by common mode gain. For this differential amplifier, CMRR is infinity. It is rejecting common mode signal with respect to differential signal, means infinity. That part I'll explain after this. Then we can go for different practical differential amplifier. Then we will calculate the common mode gain for that. But remember, for practical differential amplifier also, your AC gain won't change. Whatever we got now, the same thing will be getting it. Okay? Only common mode gain will change. That part we will design, and then I can say the op amp, the block diagram explanation is over. Therefore, tell me, do we have any capacitor? No, right? Except the current source. Maybe it will be replaced with practical current source or a resistor, right? There we don't need any capacitor. Because of differential point at emitter and applying inputs differential manner, we don't need any bypass capacitor. This is one of the very powerful circuits which I feel. Therefore, this is what is the motivation for your op amp. The op amp is everywhere, remember. Not the discrete op amp what you use, IC741. Even in VLSI, everywhere, you take any analog VLSI circuit, everywhere op amp is there. Without op amp, there is no VLSI circuit. There is no analog VLSI circuit. In digital, no op amp. In digital, everything is logic gate, AND gate, OR gate, inverter, NOR gate, exclusive OR gate, etc. But in analog, the fundamental building block is nothing but your amplifier. Okay. Now write down CMRR definition. CMRR is defined as common mode rejection ratio. Okay, is equal to, it is defined as differential gain divided by common mode gain. Differential gain divided by common mode gain. Ideally it should be infinity. Ideally it should be infinity. But if you take the ideal differential amplifier, what is common mode gain? 0. Differential gain same as C amplifier. Therefore something divided by 0, infinity ideally. But practically it is not infinity, because practically it is some differential gain, some common mode gain. Therefore the meaning of CMRR is, with respect to common mode gain, how much is the differential gain? Common mode gain is expected from practical circuit, but the differential gain is expected very high. If differential gain is very high with respect to common mode gain, kind of rejecting common mode signals with respect to amplifying differential signals. That is the meaning of CMRR. Okay. Therefore, this is what, if you write CMRR in dB, therefore CMRR in dB, this is absolute definition, which is ratio. If I convert into dB, which is nothing but 20 log differential gain divided by common mode gain, right? Therefore log A by B, log A minus log B, 20 log AD minus 20 log common mode gain. Therefore this is nothing but differential gain in dB minus common mode gain in dB. This is what is the definition of CMRR in dB. Okay, and this is the fundamental definition of CMRR. Take this. Then after that I will explain practical differential amplifier. Then we can define the same thing for op amp also, because your op amp is also dealt with differential gain as well as common mode gain. But in the case of op amp, the differential gain is too much because of two stages. Common mode gain, because the first stage itself is limiting your common mode gain, overall common mode gain is also limited. What it may be, for op amp also CMRR is defined. For any differential amplifier, we can define CMRR. Over? Okay. Now write down practical differential amplifier. Practical differential amplifier. Okay. Practical differential amplifier. Just listen, don't write anything. Instead of current source, you can add either practical current source or a resistor. Let me say this is your RE. Now this is your VCC. This is RC. It is equivalent to practical current source, internal resistance, or the physical value of RE, whatever you are using. When I say C with RE, whatever RE you are using, right? That is what your RE. And now this is what your V01 and V02. This is V1, V2. This is transistor 1, transistor 2. Okay. Now let's do DC analysis first. Then we will see AC analysis. Okay. Now DC analysis. When I say DC analysis, okay, just listen, don't write, I'll give you time. Here, when I say this is RC and then RC, I want to find common mode gain, okay. This is what is your VCC, right? And now this is what your V01 and V02. Then this is your V1 and then V2, right? Now let us apply only DC signals. When you apply only DC signal, let us say this is your VCM, a common mode signal. This is also VCM. Then because of VCM, right? Then whatever current you are getting, this is what your IC. And this is also IC. Right? Then whatever current you have here, it is not I bias. Earlier it was current source, but now it is not current source, right? There is a current. Let us say this is what is your IE. Now what is this current? This is not IE. This is what is our tail current source. It is I bias only, but this I bias is not current source. This is what is I bias by 2. Similarly, this is also I bias by 2. Okay. Now let's see. If you increase the common mode voltage, common mode is both are increasing, not a differential way. This is common mode way. Changing, V1 and V2 are changing, but in the same way. This is nothing but common mode signal. Okay. Therefore, both are increasing or decreasing. If this is what is the scenario, then tell me what about your IB? IB will increase. This is what is having IB. This is IB. And this is also having IB. Okay. IB, and this is IC, and then V01 and then V02. Therefore, we are expecting this is V01 and then V02. Therefore, this is V01 and this is what is V02. We are expecting output should have VOCM. Both are same because both are same currents. Now, if both are increasing, when both are increasing, can I say your IB will increase? Right? When IB is increasing, right? Let us say it is increasing by some delta 1. Here IB is also increasing by delta 1. Then your IC is increasing by, let us say, delta. This is also increasing by delta. Then your I bias is increasing by delta. This is increasing by delta. Then whatever you are having, current is increasing by 2 delta. Here this is not a current source. Earlier it was a current source. Because it is not a current source, it is allowing the current, but I am expecting the effect now. Now when this is what is increasing, now earlier I bias into RE, that was VE. Now I bias plus 2 delta. Now the voltage, the current which is what is flowing through RE is increasing. Then VE will increase. Negative feedback, because this is nothing but a negative feedback resistor. Remember, this is negative feedback resistor. This same thing like your CE with RE amplifier, negative feedback resistor. Now when this is what is increasing, then what will happen? Because of this, now your VE will increase. Now negative feedback will come into picture. Now when VE is increasing, then what will happen? Your IB will decrease, means your delta 1 will decrease, both the cases. Then your delta will decrease and this will decrease. Then your output voltage, whatever may be, how much is the increase in IC, If same amount of IC is decreasing, then it is perfectly compensation. But what is the guarantee that how much is the increase in IC, the same amount of IC is decreased because of the feedback what you have? It is exactly same as C with RE amplifier, right? For that we need to do mathematical analysis. Qualitatively I cannot say that it is compensated 100%. That we cannot say. For that we need to do mathematical analysis. Then we need to calculate common mode gain. Therefore what is common mode gain? Common mode gain is defined as ECM is equal to the change in V01 due to change in V1 or change in VCM or change in V02 divided by change in common mode voltage, where VCM is nothing but V1 is equal to V2. Okay, take it. Then we will derive what is common mode gain using mathematical analysis. That is also straightforward. Once you know the definition, that is also straightforward. Okay. Almost 5 to 6 minutes time is there for the session. Then you try to draw this. I am not disturbing the original circuit. This is what is the original circuit, but we are doing DC analysis. Therefore for DC analysis, this RE is not completely rejecting the change in IC. It is rejecting but not completely. It is same as C with RE amplifier. Now we need to do what is the common mode gain. Ideally we want common mode gain to be 0 or as minimum as possible. Okay, let's calculate that mathematically for the practical differential amplifier. Ideal differential amplifier is nothing but instead of RE there is a current source. That is ideal differential amplifier. But ideally we don't have ideal current source. Either we have practical current source or a resistor. Take it. Then maybe I will derive what is common mode gain. Then after that we will see the AC analysis. With that differential amplifier is over. Okay, I'll come in a minute.